For the exam, and then we'll finish writing our level order dealy flippy thingy. All right, so I think the class average on the exam was like a 75, 73, something like that. All right, so why are arrays considered to be fast and linked lists considered to be slow? So something along the lines of arrays require contiguous memory so their positions can be calculated, where linked lists are memory efficient, but are slow because in order to traverse the list, we have to start from the beginning or the end of the linked list and traverse from node to node to node as we go through the list. So something along those lines, definitely contiguous memory needed to be mentioned. All right, what is an intent as it relates to Android programming? So an intent is an object that is used by an activity to launch another activity. Then you can also package information along with an intent to send to destination activity. So something along those lines, that it's an object used by an activity to launch another activity. It's not the launcher itself. Let's see. How much space in memory does a 20 bucket int array take? This was one that was missed a lot. So let's... So 20 bucket int array. So we have to think about, so if we were looking at that, that's int array AR is equal to new int array 20. That's kind of what that guy would look like, right? So what's that doing? It's building enough contiguous memory to hold this many of these guys. All right, so how big is an int? An int in Java is 4 bytes. All right, or 32 bits. You can think of it either way. 4 bytes, 32 bits. So that means this would be 80 bytes of total memory to store a 20 int array. So you need 20 positions, each capable of holding 4 bytes. Make sense? All right, so that's that one. What is MVC and how is it implemented in Android programming? It's the model view controller, which effectively says keep your interface separate from your logic. It's implemented in Android by using our activity controllers. So we have our code on one side, and then we have our XML documents on the other side that actually represent our layouts. And then those guys are linked together through unique IDs. All right, so we can, for instance, access a label, a text view on our Android interface by its ID inside of our code. Similarly, we can also handle events with like on-click listeners. All right, what are the 3 methods that a stack must support, and what does each one do? It's push, pop, peek. So push adds a new element onto the top of the stack. Pop removes the top element from the stack and returns it. Peek returns the top element of the stack without removing it. All right. That one was actually missed more than it should have been. All right, write an error-free hello world program. I'm not going to write that, but just do it right. I think most people got that one correct. All right, so for the next questions, you can assume there exists a stack and a linked list object that are capable of holding integers. You can make reasonable assumptions regarding the methods that each of these data structures already have. All right, so number 7, write a method named reverse list that takes a linked list as a parameter and returns a new linked list that is the original in reverse. That's probably not the way I want to go here. All right, so this guy is going to be called what? Reverse list, and it's going to return a linked list. So linked list, reverse list takes a linked list as a parameter this down a little bit. All right, so starting point, you should definitely have been able to write that aspect of it. All right, that was probably worth a point if you could at least do that. All right, so what are we supposed to do? We're supposed to take in this linked list and return a brand new linked list that is this guy in reverse. All right, so depending on which method you assumed existed, so for instance, maybe we have the count of a list, maybe we have the, maybe we can get an element at an individual bucket in a list. We're going to go ahead and create a blank linked list. That's going to be our answer. So linked list answer is equal to a new linked list. Now we need to go through every element of our first linked lists from beginning to end, and we can continue to add front of our new linked list. All right, so maybe we say for int I is equal to 0, I is less than lst dot count, something like that. I plus plus. And then we'll say answer dot add front lst dot get position I. Something like that. So we'll continually add to our new linked list from the first position. We keep adding onto the front of it, which will push the very first element towards the end of it. So effectively treating it like a stack. Then at the very end, return answer. So something like that should get the job done. Questions on that one? Okay, next one. Write a method named remove at index. It takes a stack and a zero-based index as a parameter, and it should remove the element at that index in the stack, leaving the rest of the stack intact. All right, and it just mentions that position 0 in the stack is the top of the stack. Okay, so remove at index. Let's just copy this whole slide. And it's supposed to return a new stack. The stack has no zero-based index. Should remove the element at that index in the stack, leaving the rest of the stack. Okay, so we don't need to return it. So this is going to be void remove at index. It's going to take a stack x and an int index as a parameter, and our job is to remove every element. Remove only the element at stack at position index in our stack S. So what we need to do, since stacks only have 3 functions, push, pop, peek, is we're going to need to pop from our stack over and over and over again until we reveal the index that we want to remove. Make sense? Then we need to put everything back. We need to pop that guy off and put everything else back on. So we're going to need a temporary stack to hold on to our things that were taken off. Stack temp is equal to new stack. All right, so now we want to go through all the way up to but not including index. All right, so if index was 0, for example, we want to make sure that we stop just short of that. So for int I is equal to 0, I is less than our index, I plus plus. And what we're going to do here is we're going to say temp.push s.pop. So we'll pop from S, pushing it onto temp. When we're done with that for loop, we should be in a situation here where we have a the very top of S should be the guy we want to burn past. All right, so we'll just say s.pop and not put that value anywhere. That effectively removes it. All right, now we need to put everything else back onto S. So we might say while temp.peak is not equal to null, or if you wanted to assume that there was a is empty or something like that, that's fine. So while temp.peak is not equal to null, we're going to say s.push temp.pop. And that should put everything that we had removed to unveil the guy we wanted to get rid of back onto the original stack. Make sense? All right, so something along those lines. Again, you may have taken some liberties in terms of what functions were available, but it was an unreasonable assumption to say s dot remove that index. Just one liner didn't fly. All right, especially in light of the question before that. So let's just get rid of that. It's no longer a stack. It's whatever I need it to be for this question. All right. Next. Okay, that's the end of the programming ones. Now it's just telling me what these guys do. All right. I thought I asked harder programming questions than that. Weren't those both pretty easy? All right, so number 9, what does the following method do? So stack do something, takes a stack as a parameter. Okay, we create a brand new stack. As long as the parameter stack is not empty, what do? We're going to push onto temp stack, s.peak twice, then s.pop. So this effectively reverses s, but creates duplicates of every entry. So in the end, temp stack is s in reverse with every element from s doubled. Make sense? All right, so that's number 9. Number 10, what do the following method do? I think before I had it in a section where it says, what do the following methods do? And then I showed you the 2 separate ones. So, yeah, that's some grammar issues there. So what does the following method do? It's called do something, takes a linked list and a pause as a parameter, returns a new linked list. So we create a blank linked list called answer. Okay, so I tell you that there's this method called get node, returns a node without removing or disconnecting it. So we're getting something from a certain position in our linked list that's equivalent to our get guy right here that I said exists. All right. So get node at a pause, and we're going to store that in cur node, and then we're going to take our new blank linked list and add to the front of that the cur node, the guy we just grabbed from our original linked list, and then we're going to return answer. So the question is what is the nature of answer? Answer is effectively a sublist of the original list. That is to say, it's everything from that node and everything that was connected to that node from the original list is now inside of answer. That makes sense? So this is effectively, for linked lists, the substring method. All right, questions, comments, concerns, bribes about the exam. If you have questions about how I graded it, come up after class. I'll tell you why I took points off for whatever, and then we'll go from there. But that was the exam. All right, so now let's talk about our homework assignment. All right. So homework assignment was to finish implementing our level order dealio. How'd that go? Not too bad. All right. So, I think I did software updates on this guy. Let's see what broke. So if I remember correctly, we already had a bunch of comments in there. And so telling us what we needed to do, we were pretty much able to just follow those comments, and it just magically worked. Okay, so this is in our BST. Here we are. You learn so much hardcore material in your classes. I just heard him say. He must be talking about pre-sem. Pre-sem is a hard major. You got to take all these like foreign languages. That's why I can't believe you do it.
2 and 3 right now. It's terrible. It's every morning at 8 o'clock.
Yeah. Well, so that's why it's terrible. It's in the morning. So not only are you not an outdoors person, you're not a morning person.
I just don't want to be like thinking that much that early.
So what are you going to be doing when you have to give like a morning sermon to your flock? To your flock? What do you mean? Who you think somebody else is going to write it? You're going to have to write that thing.
I know. I'm going to write it. I'm saying it's already going to be written. I'm not going to write it in the morning. Yeah, I'm not going to be writing it the morning of.
Okay. So you're not going to write it in the morning of.
Citing it, which is different than learning all these weird rules about participles and stuff like that. It's weird.
Yeah, see, I just can't imagine you being like very good at Greek and Latin and stuff.
I'm actually okay at Greek because I took German before this.
Okay.
So they said learning another language really helped.
Why hasn't that translated into your Java skills?
Those don't use changing verbs. Well, I guess they. It's not the same.
I think I just lost my latte. Or my macchiato for next. Oh yeah. Yeah, I wouldn't want to do that as a major. All those hard languages.
The terrible part is too. So I already started learning this, and they just announced that you're now going to be able to learn the languages at the seminary instead of needing to know them coming in. So it's like I could have just put them off.
Well, that doesn't make any sense. Like, oh, I'll just kick the can down the street and I'll learn it. I'll not learn it later. I mean, I can only assume that when you're actually at seminary, the classes are probably, it's like basically a master's degree, right?
Yeah.
It's a MDiv.
Mm-hmm.
So, when you're at seminary, it's probably a fairly, rigid type of, curriculum. Do you also want to be learning these languages then?
No, but if you already have them learned, you still have to take like other language stuff there.
Well, so you know more languages then.
Yeah.
So then you'll actually be like a functional pastor. Instead of what I suspect you're going to be at 8 in the morning. Based on complaining about your Greek class at 8. So what do you get? You get up like at 8:05?
I'm actually I'm like 2 minutes late every class. So I get up at like 7:45. But there's like half our class is usually missing because people just don't wake up and show up. And all we do in class is go over our homework.
And these are future pastors.
Yes.
Skipping. Gone. Nada.
Talk to them. He hates our class too. There's like 3 people who have no idea what's going on in our class.
Who's the teacher?
Mudge.
Okay.
There's 3 people who are just like totally lost. And it's kind of funny when it goes to them.
Couldn't you see him as a ninja?
Yeah.
You know what I mean? Like that statement shouldn't make sense, but it kind of does. Yeah. Couldn't you see him as a ninja? Or maybe Daredevil. I can see him playing Daredevil.
I haven't seen Daredevil.
But you know of him. Or is that too outdoorsy? That's too outdoorsy for you?
See, I want to get into that type of shows like Arrow and Flash, but I just don't have time to.
Well, because you're sleeping all morning long.
I sleep until 7:45.
That's pretty late.
No. My one roommate, he has it nice. He doesn't have class till 1 o'clock, so he wakes up at 11.
Wakes up at 2:30. I've had those students. One of them's name is Steve Caruso. Is that your roommate?
No.
All right. So let's look at this guy. All right. So visit level order. We created some stacks to work with here, right? If we don't have anything to visit, we're just going to say empty tree. Otherwise, we have some stuff to visit. So we'll go ahead and we'll push the root element onto our child stack, and now we need to process the child stack. So what's the first thing we do? We clear child stack by adding its children to temp stack and then popping. So we push the left and right children of peak child stack onto temp stack. So we probably should go ahead and get the top of it. So we can ask if child stack dot peak. So if we're in here, we know child stack has something in it. So we know child stack dot peak is a thing. All right. So if that guy dot get left tree is not equal to null. So if we have a left tree, then we'll go ahead and say temp stack dot push child stack dot peak dot get left tree. So that'll make sure that the left child, if it exists, gets pushed onto child stack. Then if child stack dot peak dot get right tree is not equal to null, temp stack dot push child stack dot peak dot get right tree. Okay, so that'll add the left and right children of peak of child stack onto temp stack if they exist. Then we need to pop from child stack and push onto content stack. So content stack dot push child stack dot pop. All right, so that should fulfill that part of it. So this is going to go through and clear out child stack by pushing the left and right children of each of its nodes onto temp stack, and then ultimately removing the top of child stack and adding it to our content stack. We've done processing it. Now we quote visit it or put it in the queue to visit. All right. Next thing is we move the contents of temp stack onto child stack in reverse. So that means we pop push onto child stack. So child stack dot push temp stack dot pop, as long as temp stack has stuff in it. Okay. We now know that that child and temp stacks are empty, because what's happened here is this loop ends when both of those guys have nothing to process. All right. When child stack has something in it, we know temp stack might get some stuff put in there. But as soon as both of these guys are empty, we've completed processing everything. Okay. So all our nodes are in content stack, but in reverse order. So we need to reverse them again, unless, as we mentioned last class, we wanted to deal with, for instance, maybe we have stuff in, we're searching news stories, we want to see what's most recent. Maybe we don't reverse it then, because then we'd be visiting in level order from bottom up. All right, so we're going to pop push onto answer stack from content stack. So answer stack dot push content stack dot pop. Our final answer is answer stack, and we can visit the nodes in pop order. All right, so we just go through answer stack, and what? We're going to print out the payloads. Is that what we're doing? Is that what visiting means for us right now? Okay. So we'll go ahead and we'll say while, oh, we're already in the answer stack, not equal to, is not empty. So we'll say system.out.print. Do we do that? Do we do prints or printlns for the other ones? I think prints would all on one line.
Yeah, but you can't do prints in Android Studio.
Oh, that's right. So do we just built the string and then did a single println. Okay. we'll say answer is equal to, well, let's just do answer plus equals answer stack dot pop dot get payload concatenated with maybe a tab, and then ultimately we'll do a system.out.println answer. Like that. All right, so now back in our main activity, here's our visit level order, which should match up since we built our, I was showing this in another class. You know underwater hockey is a thing?
Yeah.
That's a real sport. Do you do water?
Yeah, I don't mind water.
So as long as it's indoor water.
It's like chlorine water, yeah.
Yeah, not out.
It depends. It's like we had to do it in high school. That's disgusting. You know how many people have been in there all day?
I don't keep count, but I assume you do.
A lot.
A lot. Okay.
Our high school was like relatively decent size, and like when we did swimming, everybody did swimming.
All right, so you'll do pools as long as there's chlorine in it.
Yeah.
And it's indoors. Will you do an outdoor chlorine pool?
Yeah.
All right, but it's got to be away from foliage.
Yeah.
You can't. Like, you would.
Well, like in the middle of a tree.
Like the tropics. I think it's like a. You
What
know,
if it's warm outside? I don't like it when it's like super warm.
or if it's too cold.
What if it's cold? You can always bundle up more. Like when it's hot.
When you're in the pool,
Well, yeah, obviously you're not going to swim. in the
explain to
freezing.
me how you bundle up for the pool.
We're like a scuba diving gear. I
I
didn't think you meant
can see you at like at a hotel pool, getting your dry suit on. Yeah. All right. Here's our level order. So given our current set of things, we should get this list of stuff, right? Because we set up our tree to match this example. All right. So let's see what we get. Yeah, I mean, like the condo I rented in Florida for next winter has, like, the pool has palm trees all around it. This might as well be out in the middle of nowhere. His pool is on the beach. There's no chlorine in that. There's salt.
Why?
But you know, a lot of like gyms and stuff now have moved to saltwater systems.
My aunt does that. It's weird. She lives in Florida. She's like an environment freak.
So she does what? That's weird.
The saltwater thing for no reason.
A lot of gyms have done it. It's better for people.
She's worried about the environment.
Well, but I don't think it's just that. I think it's better for like your skin and stuff. Than
Like your hair feels weird after you get out of the chlorine pool.
Yeah, so doesn't that support what I just said?
Yeah. That's what I'm saying.
It's,
But why would you have a pool by a beach? I don't get it.
well, no, it doesn't. His pool is the beach. Well, it is the ocean. That's where the pool is, right? There's a pool. Yeah, but that's not on the beach. It's you have like hotel stuff, then pool, then beach, then ocean. That's like how the sandwich is made, right?
But why? Why not just go in the ocean?
Well, I mean, he probably does. You go in the ocean, right? You usually go to the pool. Oh yeah, I see.
Oh, well, if there's a hot tub.
Yeah, but when you live in Florida, cold for you is like 84.
Yeah.
It's like whoo. It's like 72 degrees outside. My grandma looks like it's like January in Wisconsin.
Yeah, some of my
She is putting on layers.
And they come up for winter, and they put on like 5 winter jackets just to like take a walk down the street somewhere.
I golfed down there. This was a couple of winters ago at TPC Heron Bay, and it was like, I don't know, 65 degrees out and a little windy with some rain. So I show up in a polo and shorts. It's 65. Okay, the starter, looked at me like I was absolutely out of my mind. Like he didn't know if they should like on the third or fourth hole send somebody out to find me due to like exposure. Like I was going to be dead due to exposure. And it was in the 60s.
I golfed in like 40-degree weather while it was raining over Bray.
Wait, you golf?
Yeah.
You know, that's an outdoor sport.
Yeah, but those are like nice cut grass. You don't have to like go near trees or weird plants. Oh, the one time I did golf.
Florida, there's alligators on the course.
In Florida, I got attacked by some cranes. That was really irritating. I'm pretty sure I told you this last year when we were talking about golf. Those were not nice. So I just left the ball there and moved to the other side.
Attacked by cranes.
They were these giant. They were like 4 feet tall. They weren't like small birds. But like, because I started trying to walk there, and they were not having it.
It was attacked by some cranes. All right, let's see. We got FBG ADI. Is this right?
That's right.
FBG ADI CEH. All right. So paint by number works pretty well. So lesson learned from last class. Spend a lot of time designing your algorithm first so that when you actually go and write it, this was fairly trivial, right? We just were able to drop our comments right in and it just worked. Okay, so questions about level order traversal. All right, so now at this point we've looked at various ways that we can actually walk through a tree, but we have to talk about the nature of the tree to begin with. Because if we're actually searching for a value in a tree, at this point we're just saying, here is the stuff, here's the way I can walk through the tree. We're not actually searching at this point, we're just going through the tree, but we can certainly throw an if statement in somewhere and say, is the node I'm visiting right now the guy I'm looking for? If yes, I'm done, found, something like that. But we have to think about the nature of, I'll go here. These trees are pretty balanced trees. Well, they are actually all very balanced trees. So when a tree gets out of balance, so we want to look at AVL trees. Let's do the search here, because they'll show us a tree that's out of balance, I'm sure. Yeah, something like this. Okay, so a tree that's out of balance means that the depth of the left side is more than 1 off the depth of the right side. Okay. Now they're actually doing where it's even well, this is more than 1. So the depth over here is, we'll say this is 0, this is 2, so they need to do a rotation. All right, because the goal ultimately is to have the tree in balance. So if your tree currently looks like this, we're going to say that that tree is inefficient to search. All right. So we want to put it into a position where it is efficient to search. Generally speaking, it's still going to depend on what algorithm we're using to actually do the search, but you know, that's kind of the scoop here. So we have 2 different ways of doing rotations. So the different ways that there's kind of 4 different ways that our tree can be out of balance. All right. In the left-right case, it means that the left side of the tree is the side that has a greater depth than the right side of the tree. But it's actually the right side of the left side that is causing it to be out of balance. That's the offending party. Okay? So that's the left-right case. So we need to be able to identify how a tree is out of balance to begin with. So we'll talk about this at a high level, and then we're going to look at how do we find out, how do we first ask the question, is this tree out of balance? Then how do we ask the question, how is it out of balance? So I can make the appropriate rotation, the appropriate fix. All right, so it's either out of balance this way, assuming it's out of balance, or it's out of balance in the right-left case, that it's the right side of the tree is the one that's out of balance, and specifically its lowest left tree is the guy who's actually out of balance. All right. Or we have left-left case and right-right case. These are the easier ones to solve. Left-left and right-right. In fact, you see, when you have a left-right case, what your first step is to do is to turn it into a left-left case. So this is a 2-step rotation to go from here to here. It's a 1-step rotation to go from here to here. So in a left-left case, it's the left side that's offending and it's its left subtree that's offending. So that's an easier rotation. You only have to do part of the steps. All right, so a couple of things to consider here. Let's kind of add some stuff to our slides. We talk about AVL trees. This is known as what's called a self-balancing tree. All right, there's a couple of other self-balancing trees. Let me just show you the other one at the high level here. I like to use AVL trees as our example, but there's a called a red-black tree. Just want to see if they give a list of self-balancing trees somewhere in here. They don't. Red-black tree. All right, so a red-black tree is another kind of self-balancing tree, pretty similar to AVL tree, just a kind of a different take on how rebalancing happens. What they do is they, it kind of becomes like a checkerboard. They mark different nodes with different colors, and how a node is marked is then used to determine how to rebalance it. Just a different approach to this. I'm not going to go into the algorithm for this, but I find red-black trees to be less useful. AVL trees are typically the ones used by a lot of, well, actually evolutions of the AVL tree is used for database systems. So in database systems, we have something called a B tree, self-balancing tree data structure that keeps data sorted and allows searches, blah, blah, blah. So these guys, I like to think of as kind of an evolution of AVL trees. They take it to the next step, and these are actually the kind of the heart of our database management systems, modern ones. But now we're moving away from that with our no SQL type data storage systems that no longer try to structure your data in an efficient way. Now it's all about speed. How can we access our data as quickly as possible regardless of how it's stored? So this would be the data structure behind Oracle and MySQL and Microsoft SQL Server, those guys, but probably not the data structure, well, actually definitely not the data structure behind things like Amazon S3 or Google App Engine or different cloud storage, Microsoft Azure Cloud. Is it just cloud storage? Microsoft Azure Cloud Storage? I think that's all it is. But in any case, these are all self-balancing trees, which means that as we add stuff to our tree, the tree then asks the question after each add. So the first thing that we should be thinking about here is inefficient in terms of performance. Okay, so there's a trade-off. To make search fast, we have to keep the tree in balance. Keeping the tree in balance requires potentially rebalancing after each, let's just say after each modification to the tree. We really haven't talked about removing things from a tree. I mean, it's no worse than the other stuff we've talked about. Just I want to get through as many data structures as we can. But every time we modify the tree, that potentially has thrown things out of whack, and therefore we need to update the tree. And rotations are expensive, as we're gonna see. And the more importantly for you, the rotation assignments are hard. So that should be fun. Good. We should do one over Easter. How much money do you have in your wallets? Since we have a couple of future pastors in the room, let's hand around the collection plate. That would be pretty funny. All right. So we'll see where we get to today. I may be inclined not to give you an impossible assignment over break. What was I talking about? Oh, yeah. So keeping a tree in balance is expensive. All right, we need to possibly change it every single time we add something. So we do need to keep this in mind. If we have if we have a collection of data that we need to search often, it would be in our best interest to search it fast, in the fastest possible way. Therefore, keeping that tree in balance would be important. Having said that, let's say that same data set has information added to it very often. And the approach that an AVL tree typically takes is that every single time we do an addition to the tree, we then rebalance the tree if necessary. So if we have a giant set of data, and let's say we're adding 1,000 new elements to it per day, that means we potentially rebalance that entire data structure 1,000 times per day. All right. Now, and I promise you that's expensive to do that. You know, for those of you who've had the operating systems class or one of the other classes that we've talked about, this thing called context switching, it's pretty similar to that kind of evil. All right. It's a very expensive task. It also puts the tree in a state of vulnerability. So while we are rebalancing that tree, we shouldn't try to add stuff to it. Okay, that tree needs to be shut down for business. You can't press the elevator button right now because it has maintenance that's happening on the thing. So that's one approach, is that if we're adding stuff to it very often, we can lock down the tree after each individual add. Maybe even, again, from a systems programming perspective, maybe we even use a semaphore to block access to the tree. So we're going to say, we're going to put a bouncer at the door, and only one action has access to the tree at an individual point in time. And if you want to lay a nice blanket on top of this tree, we can say only one person has access to the database at a period of time, because ultimately what's happening under the hood is there's data there, and it just happens to be represented as a tree. So only one action has access to the database at a time. So after we do an add, we then update the tree before another add or another search can occur, because that tree is at a point of flux where it's not necessarily put together real great for a period of time there. Right, so there's a lot of extra overhead that goes into keeping these trees in balance, especially in terms of their actual application there's plenty of applications of trees, but the one that's most familiar to us is going to be databases. All right, that's a kind of a perfect application of it. Another approach might be, one of the reasons why we're saying we want our trees to be balanced is because we want them to be able to be optimally searched. Now, let's say that we decided we were going to keep our trees balanced on a daily basis rather than on a per add basis. So let's take somebody like Google. So Google probably has a lot of new information added to their data structures on a daily basis. And they might have a lot of information removed from their data structures on a daily basis as well. Who knows? But let's just say that their data structures change a lot on a daily basis. Now, from a pure performance perspective, which is kind of the way we're moving in today's world, right? We've talked about it from a couple of different angles, but historically, if we go back into the earlier 2000s or definitely in the 1990s, but really even just technology just a few years ago, the approach very much was about how do we minimize our memory footprint? How do we stay efficient from a memory perspective? Walking on eggshells as it relates to our computer's performance. With that in mind, it would have been in our best interest to always keep our data structures as organized as possible so that searching was efficient, especially across large pieces of data. Now, we take somebody like Google, we could probably make the assumption that Google has a lot of computing horsepower, right? So realistically speaking, if anybody could search unorganized or unoptimized, that's the better way of putting it. A binary tree is organized by definition, but unoptimized data. If anybody can search unoptimized data quickly, it's probably Google, right? Reality is by our, might it also be a fairly accurate statement to say that The more data a company is dealing with, it's probably likely that their technological prowess probably scales. So companies that we perceive are controlling a lot of data, Google, Amazon, Apple, probably have substantially more horsepower than JCPenney's, which probably has substantially more horsepower than we do on our laptops or whatever. Okay, so it probably scales. So the reality is if we are storing stuff on our own computer and we need to search through it, since we're the only user of that data and we're talking about a couple of hundred files or something like that, the difference in performance between it being completely optimized and being somewhat optimized or having been optimized within the last 24 hours is probably fairly negligible from us noticing, right? And let's kind of keep this going with more, I guess, technology jargon. How many of you have ever had to defragment a hard drive? Heard that phrase before? What does that mean, to defragment a hard drive? Usually you see a nice little picture, right? And it shows a whole bunch of individual little lines, and the lines are kind of spread across the entire array-looking thing.
Putting things that are similar together or something like that have been separated.
Okay, part of a modern defragmentation algorithm does have some of that in it. Okay, but if we go deeper than that, let's say, kind of go back near the beginning, and we're also moving away from this a little bit today because our hard drives are becoming less and less mechanical. So for those of you in here who have laptops, how many of you have solid state drives in your laptop? Maybe go the other way. Who doesn't have a solid state drive in your laptop? You got a 1950s laptop? Hey, how old is the laptop? Okay, yeah, that's probably right when it started changing. Yeah, because mine's a 2012 and it's got it has a solid state in it, but I think that was an upgrade to do that. So yeah, so in any case, solid state drives kind of bring new rules to the table, right? Because they're not mechanical. Since they're not mechanical, you actually access information on the solid state drives differently. In fact, a lot of the speed problems we have, because it seems like every 15, 20 minutes or so, solid state drives are getting faster. And part of that is because they're having to overcome the standard serial ATA interface that for years has been used to talk to mechanical hard drives. They're having to figure out, how can we make this talk in the most efficient way to this guy that's no longer mechanical? It's basically it's flash memory. It's your solid state drives it's a giant USB stick. It's effectively what it is. But before that, when we had mechanical hard drives that we maybe would want to defragment, and it's not that defragmentation doesn't exist for solid state drives. You just don't get the full benefit of it. So the idea is that when you have a mechanical hard drive, the closer everything is together, the faster you'll be able to find stuff, the faster your hard drive can operate. Because when the hard drive has this little mechanical arm called the read-write head, and this guy's moving back and forth like a record player, so to speak, on the platter, the digital platter in your hard drive. And if it's having to jump from here all the way over to here in order to find a piece of data, that takes mechanical time, right? To swing the arm from here to here, even though to a human being it's going to look pretty fast, it takes a measurable amount of time. So defragmentation takes the stuff that's split all across your hard drive and moves it towards the beginning of the drive, squishes everything together so that it's as close to the read-write head where its default position is as possible, and it doesn't have to deviate too far from that position to read stuff. Make sense? It's effectively a rebalancing of the tree. And what do I mean by the tree? Well, most of our file systems, when we think about a hard drive, our hard drives are formatted. When you format a hard drive on your computer, you usually choose the file format. So if you're on a Windows machine, you're going to choose Ntfs more than likely for your internal hard drive. But you might choose FAT32 for like an external drive, so it moves over to max and stuff like that, so that the disk will work everywhere. So kind of two different file system options for Windows, FAT32 and Ntfs. Mac, it's HFS, it's a Unix journaling file system. So Windows can't read the Mac file system. Mac can't read the Ntfs file system. They both like FAT32. Well, they both can work with FAT32. Anybody know what the weakness by today's standards is for the FAT32 file system? Any of you who, I'm sure nobody in this group, especially with a couple of future pastors, steal movies or anything, right? A lot of times those Blu-ray rips are a little bit bigger than 4 gigabytes. Huh? Well, so yeah, right, that translates is what we've talked about in here. So an int is 32 bits, right? And the biggest number an unsigned int can hold is 4 billion. So that translates into, if we actually did the math, put the commas in, 4 gigabytes. All right, so the largest single file that could be addressed on a FAT32 file system is a 4 gigabyte file. So if you try to store a 6 gigabyte file on a FAT32 file system, it'll act like it's out of space. It'll say, the hard drive has run out of space, and you look at it and say, well, I still have half a terabyte of space available. It's like, nope, not enough room for 6 gigabytes. Won't fit. Right, so that's a weakness of FAT32. At some point, they'll probably have to move to something like a FAT64 or something like that, or we're going to have a universal file system that both platforms understand. I don't know if that's happening anytime soon. Macs can almost, with a proprietary driver, can sort of kind of. Definitely they can read Ntfs. It's the writing to Ntfs that becomes a hit and miss thing. Linux has an experimental file system that allows you to read and write Ntfs, and it's probably trustworthy. It's just one of those things that they say experimental on it just in case it screws up. They've covered their butts. But punchline is Ntfs, that file system, is a proprietary file system from Microsoft. And it's built on top of trees. They have to organize their directory structure, and they have data structures in there that keep track of where files are relative to other files. And same thing's true with HFS, which is Apple's journaling file system, and don't attribute too much of that to Apple. I'm sure they've added a couple of bugs to it, but really what they did is they took it from Unix. It's a Unix file system, and specifically, actually, it would be more of the Linux file systems, because probably about, I want to say maybe mid-2000s, 2005, 2006, somewhere in there, this idea of a journaling file system became very popular, and it really kind of was born in the Linux community. Because the Linux community can foster those types of things because you have 50 different projects that are all trying to come up with the next file system. So on Linux, you can format your hard drive 30 different ways that are all incompatible with each other, so it becomes completely useless, but whatever. So the idea of a journaling file system is that when a change is made, you can roll back. You can undo horrible stuff. All right. Also, that's all done through trees. So they have data structures that live under the hood that maintain the state of information of the hard drive, including what was the last several things that happened. So that you could rebuild that. Now that's actually been going on for a long time. Through what is the name? Through RAIDs. So you can set up a RAID 2 or a RAID 0, RAID 1, RAID 2, various networks of hard drives inside of your computers. So a RAID 0 is a concatenation thing. So if you have two 1 terabyte hard drives and you set those up as RAID 0, now you have what appears to be one 2 terabyte hard drive. A RAID 1 is a mirroring technology. So two 1 terabyte hard drives can be set up as a RAID 1, which looks like one 1 terabyte hard drive, but every single time you write something, it gets duplicated across the two of them. so on and so forth. And the idea is that if you have one hard drive fail, your data isn't lost. You can pull the hard drive out, put a new hard drive in, and the RAID software, which uses various data structures, including trees behind the scenes, will rebuild the new hard drive with the data from the old hard drive. Make sense? So this stuff has been going on from a mechanical perspective for a long time. Now we've kind of built some of that technology into our file systems, these journaling file systems. But punchline here is that this idea of rebalancing trees is something we deal with all the time. But now the reason, getting back to 10 minutes ago when I asked the question about defragmenting a hard drive, okay? Do you defragment your hard drive when you're sitting there in front of the computer using it? How long does the defragmentation process take? Anywhere between 15 and 20 minutes up to a week, depending on how old your computer is. Okay. It's not a quick process, right? I mean, it's a time-intensive process, so it's probably something you would start before you go to bed at night. And because what it's doing is it's making a small change, checking to see, am I done? No, making another small change. Am I done? Making another small change. Am I out of balance? Rebalance. Am I out of balance? Rebalance. So rolling back to 15 or 20 minutes ago, when we talked about different approaches to how we can rebalance trees, a company like Google might say, well, maybe every single night, what we'll do is we'll fail over to a data backup. So any new information that's coming in during maybe the time of day that we have the least changes to our data comes in, we'll move our data over to that for the time being to collect any new requests coming in. And what we're going to do is we're going to go ahead and we're going to rebalance our entire tree for all changes that were made during the last 24-hour period, for example, effectively defragmenting their database. And what do? You say, which side is out of balance? Left side. Okay, how is it out of balance? Fix it. Is it still out of balance? Well, probably, because you've done a whole lot of moves to that data without rebalancing. So you might have to do the whole rebalancing algorithm repeatedly over and over and over again until you finally transform your tree back into something that's usable. Make sense? It's expensive. Now, obviously, from an individual piece of software perspective, we typically want to rebalance our tree after each change to the tree. That's going to be the path of least resistance. That's going to, even though it's the total amount of time, if we rebalance our tree 1,000 times, it's going to take the same amount of time. But rebalancing our tree once takes a measurable but a relatively small amount of time so that we don't have to protect our data for too long. So if we throw that bouncer in front of the door, so we're dealing with like an Oracle database or something like that, and we just added something to the database, and now the database has to re-optimize itself, and we throw a bouncer on the door, the actual physical human time it's going to take to rebalance it might be, a fraction of a fraction of a fraction of a second. Not a whole lot of noticeable time. So the bouncer just keeps people out for that, that microsecond, or that 5 or 6 nanoseconds, something like that, while it rebalances, and then the tree is now open for business again in its new, more optimized state. So when you compare various database management systems, part of what you're looking at when they talk about performance is their rebalancing algorithms and their approach to rebalancing. How did they keep the data optimized for searching? And Oracle has their own proprietary approach to that I'm not aware of, but they do something, and I promise you at some level in there, it's going to deal with tree rebalancing. That's going to be part of what they're doing, and they probably have their own little take on it, but whatever. All right, that makes some sense? So this guy goes a little bit deeper in terms of actual in practice than just, we're learning about AVL trees and we're supposed to rebalance these. These have, we aren't looking at these things just for our health. Okay? They have legitimate uses in technology. So do linked lists, so do stacks, all that stuff. Okay, so let's go back here to our AVL tree. And let's go ahead and deal with our simple case first. That's this guy right here. All right, Well, actually, before we do that, let me draw a tree. Actually, we already have a tree up here, don't we? That'll work. Probably don't want to have 6, whatever. Christian worldview. All right. Well, we got 2 passes where we got protection. We got this. All right. So we have a tree now that, actually, let's, technically, this tree right here would not be out of balance. It's almost out of balance. The right side is within 1 of the depth of the left side. All right. So I guess before we even add this, how do we find out the depth of the left and right side? So we want to ask the question, is this tree out of balance? That's the question we want to ask. That's the question we need to answer. All right. As a human being, we can look at this and say, well, because we now understand what it means to be out of balance, which means that the left side is more than 1 depth different than the right side. That's what makes it out of balance. We can look at this and say, oh, it's not out of balance. Close. It's not perfectly balanced, but it's not out of balance. But algorithmically, how do we decide whether this tree is out of balance or not? Well, we take our tree, and we're out of balance if the depth of the left side is more than 1 away from the depth of the right side. So we need to be able to ask this subtree what its depth is, and we need to ask this subtree what its depth is. And in both cases, we want to know what is your max depth. Because these trees go in different routes, right? So if we look at this subtree, okay, and this is depth 0, his left subtree is depth 1, his right subtree is also depth 1. So the max depth of this guy would be 1. Or 2, depending on how you started counting. It doesn't matter as long as you start counting the same on both sides. Okay? So this guy's going to say, well, when we ask this guy, what is your depth? Remember, that is a binary tree. Even though he's a part of a larger binary tree, he is a binary tree. So we're going to ask this tree right here what his depth is. And his depth is 1 plus the max of his left and the depth of his left and right tree. All right, so this is 1 plus max depth left, depth right. Okay, that's going to be his depth. So now we ask this guy, what's your depth? Well, his depth is 1 plus max of depth left plus max of depth right. And this other guy is 1 plus max of depth left, max of depth right. Well, so this guy has a depth of 1, right? Because he doesn't have a left or right. So this is 1 plus 0, max of 0 and 0. This guy has a depth of 0, max of 0 and 0. Or depth of 1, 1 plus 0. All right, so now these guys both have a depth of 1. 1, 1. Max of that is 1. 1 plus 1 is 2. So this side has a depth of 2. Over here, this is 1 plus max depth. 1 plus max depth. 1 plus max depth. This guy's 1 plus 0. This guy's 1. This guy's 0 because he doesn't have a right child. So the max is 1. 1 plus, so this is going to equal 2. Depth of left is 2. Depth of right is 0. Max of 2 and 0 is 2. So this guy is going to equal 3. So the left subtree has a depth of 2. The right subtree has a depth of 3. So 2 minus 3 is negative 1. Take the absolute value of it. That's 1. As long as it's 0 or 1, we're okay. This guy's in balance. Make sense? All right. Come back after break. We'll actually write this. So I'll give you a double assignment for Tuesday. I'll give you 1.5 assignments. All right. Have a good Easter. Traveling. Travel safe.